So when you're talking about from Kubernetes to chaos mesh, we really want to talk about what's the difference between failure, resiliency, and chaos. Because a lot of times we think this is the same thing. And this is something I would like to debate here, and maybe you agree, maybe not. So let's start. My name is Elad. I'm really appreciating to be here. I'm a tech lead at the CTO office at TeraSky. I'm AWS Ambassador Associate from this year, software architect for many years, and really love to do tech talks and think about technology and share it with the community and peers. So I'm going to ask you guys, what are you going to see here? What do you think? What's first thing come to your mind when you see this architecture? What do you think? Like amazing, boring? How the hell I'm going to manage it? What do you think? So there is a lot of microservices here. There is a mix of communication styles. As you can see, sometimes I can create an ASCII call, sync call. Sometimes I'm just going to push some kind of event into the topic, and someone reactively will going to handle it. So there is a lot of different communication styles. Of course, there is heterogeneous storage type, because I'm using database, S3, I have my Redis, I have my Rabbit, blah, blah, a lot of storage layers. And of course, in order to spice it with even more, let's add multiple databases, multiple cloud vendors. And I have Twilio, I want to send email or communicate with the customers. And the last thing is that in order to support it, I have a lot of data pipeline, ingestion, CI/CD, and a lot of things that are running, crunching data behind the scene. So I think when you're coming to your office and see it, maybe you're going to say, okay, so boring is, I don't want to be boring today. Of course, this is going to happen with this architecture. But again, for a complex system like everyone is using today, this something can happen. And I think that because we are stuck in going from day to day, I want to discuss about the illusion, in my opinion, just my opinion, the illusion about stability and when everything is failing. So why it's happening? It's happening because we embrace microservices to the edge. And it means that every team in a lot of companies can build their own deployments, artifacts, and CI/CD parts independently. They can use different stack, because now when I'm managing my own domain, I can make decisions like I want to use Java, I want to use C++, I want to Golang, but I have a new project, why not I'm going to use TypeScript? And it makes it much more complex. The second thing is that because it's my own domain, I will manage my own monitoring observability. And I just interviewed a very big company that we done some kind of review of the architecture, and we saw that they have like 12 data silos for monitoring observability. And the first time they have any issues that crossing between these kind of teams, they even need to go to specific URL to use New Relic and then other time Dynamo Trace and correlate the data between themselves. It's really the definition of creating data silos. And I think we convinced ourselves that complexity equals robustness. I'm not sure if this is the case or not. Why it's happening? It's happening because we are still struggling to understand what is a chaos. So for most of us, when we're talking about chaos, we don't really understand it. For us, we have a failure mindset, which means that if something breaks, I'm going to investigate it, I'm going to fix it, and if I want to be very thorough, I'm going to create a test for it. It's going to be integration, unit, but this is a flow and repeat. Things happen. We try to predict by creating our integration test, unit test, and blah, 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 sometimes stress, penetration, whatever. But if something happened, we react to it. We fix, and we continue the loop. Second, if you're going to ask your management, they're going to tell you, okay, if the system is really robust, let's plan it to be robust ahead of time. Please just do it. Don't talk to me about chaos. And the last thing, when you're talking about SRE guys, they're going to tell you, what the hell are you going to do? You're not going to mess with my production environment. Chaos will just create chaos. It's not going to solve anything here. Do you agree? This is really hard to explain sometimes. So let's try to imagine a company, okay? And there is a major outage in the company. It's 5 in the morning. We're getting an statement that's all across all the continent. There is a DNS issue connecting into the site. We do not understand what's happened. We send our engineers to the data center. They're just trying to get inside, but something happened. And even the locking door itself is locked because of the same system. This is an issue. This is something they cannot predict. But now, because you cannot enter the data center, you cannot get into the office, you cannot get to the data center and understand what's happened. And this is exactly what happened in 2021. This is a tweet from Shira Frankel that says he just spoke with someone on Facebook, and they tell us that they literally cannot get to the office to solve a major issue. What was the issue? It was they changed some kind of a BGP routing in the major infrastructure. It caused disconnection between, of course, the internet and the rest of the client itself, but also the DNS was unable to communicate. So Facebook was down for more than 6 hours. But because it was so disruptive, the only way to fix it was to get inside the data center, connect locally, but it couldn't get into the office itself. So this is something that, we cannot predict. And this is some kind of chaos. But the next one, I think it's a bit more obvious. And we see it from time to time. Okay, now it's X. Before it was Twitter. Something went wrong. And again, it was some kind of issue in Twitter infrastructure. But what was the root cause? So, of course, they have engineering, they have war rooms and the incidents, and they're trying to figure out what's happened. So take a look here of Elon Musk tweet 4 days before the accident itself. So fractal Rob Goldberg machine is what feels like understanding how Twitter works. It was like a bit after he purchased Twitter, and he tried to say to the engineers, this is really, really complex system, over-designed, over-complex, what the hell are you doing it? And just a few hours after writing it, he says the next one, which is, I think, can be related to the issue. It's amazing it's working, even after I disconnected one of the more sensitive data centers, data racks. So as you see, 4 days after, the complete Twitter infrastructure crashed. So I think we can understand sometimes error, it's not something we can predict. Chaos can be someone actually taken out, and this is a real case. It's not like the real tweet, but it's really happened. So why are systems, and especially distributed systems, are doomed to fail? As you see here, this is a series of distributed systems. It's describing 8 items that we cannot predict ahead of time, but can jeopardize the stability of our system. Let's try to focus just on 3 of them, for just an example. Take a look here. The network is secured. This one is actual shares that you can buy at Amazon, describing the famous sentence from Amazon CTO, dance like nobody watching, but encrypt your data like they do. Because as you know, behind the scene, even AWS infrastructure, even the VPC are just virtual. The same technology, the same thing. And for you, and this is what he said, and this is his mantra over year, it's the main thing. If you want your data to be kept secure, you have to understand that 100% of the time, data can be captured. The only way to prevent it, if you secure your keys, all right? So the only thing that if someone in the middle trying to take the data, he will not be able to decrypt it because he don't have the encryption key. This is the only way to secure a network. Another thing is bandwidth is unlimited. Of course it's unlimited, but if you have 2 nano instances communicating with each other under very, very high burst, it's not going to give you more than 50 Mbps per second. It's not going to work. So there are issues that you need to think ahead of time. And the last time is that we really think that transport cost is 0. And this is actual customer of us. And as you can see here, it predicts 6K monthly for egress communication. And again, the developers, the DevOps, and even the engineer and the architect didn't thought about it. It doesn't matter to them that they have some kind of egress communication to the internet to fetch very important data. But as you can see here, based on the region, and this is taken from June 2024, last year, it's a lot of information, and it's really cost. So let's discuss a bit about our toolkit for resilience. So of course, we started with Kubernetes. This is de facto or basic for provisioning any cloud-native application and manage it. And it's great. It's a foundation of everything else. It's giving us a self-healing capability throughout controllers and conciliation loops, controllers who can write our own business logic. And a lot of time when I work, for example, in JFrog, we created controllers, operators to manage a healing system that was specifically for the JFrog products. Another thing is we have, of course, liveness, readiness, topology awareness, replica affinity, pod disruption budget. all giving us the ability to create a topology that could be self-aware, very robust. But it's not enough. It's not enough because when things do break, and I'm hoping that we're a base now that things will break, is that Kubernetes alone is not enough, right? If I want to do rollback or do something else. So in order to do so, let's add another component to our architecture. It's going to be GitOps. So I have a developer. It's going to push the code into the Git with, of course, the code itself, but also the metadata about the deployments that I'm going to do. And of course, ArgoCD or Flux will be able to fetch this data using the same reconciliation loop as we're doing in any other applications that we are working with. And of course, we'll sync the server to the latest and update states. And if I need to roll back, it's going to do the same. And again, this is a resilience issue. It's not just about deployment. It's a single source of truth. All the desired states live now in Git, not across scattered repository, CI jobs, CD jobs. As we said, one of the fallacies of distributed computing is we have only one administrator. If something happened, I want the responsibility of the developer to do the same. I want him to push another version, right, and send it into the CD, into the GitOps solution as a unit, like Argo Flux CD, and be able to automatically do the same thing and recover for something that happened. Another thing is, as we said, it's instant rollback. I just need to do git revert, and the sync will be automatically. And the last thing is auto drift repair. As we know, drift can happen. It could be all based on infrastructure, also in Kubernetes. We want a mechanism that will help us to detect the drift and also remediate them automatically. So this is our resilience architecture so far, but we're still missing something else. What about observability? If we're going back to what we discussed before, observability, and again, it's happening, and again, we interview a company, more than 300 developers, around 200 microservices. They have their own solution for monitoring. Some of them even heard about observability. They just have, for example, logs in Splunk. So in order to do so, I think that the main way to do so is without intervening of the systems, the developers, or hopefully anything in my infrastructure too much. And again, I know that I'm oversimplifying it. But what Pixie is doing, it's an eBPF-based instrumentation of with zero code-based changes. So, for example, I was Java developer for many years. And in the old days, when I need to do some kind of orchestration, I use CG or any other libraries, and I orchestrated the code in order to get some metrics that wasn't exposed directly to the system. And of course, now we have it with other technology like hotels. They have a lot of instrumentation agents can be in any common language that we use today. But again, here, it's another layer. Because you use it at the core level, at the OS system level, we can run eBPF on Linux environment without any code change. And it's giving us something much more enriched and much more dimension of data. We can have capturing the network flows, application metrics, and resource usage. And all of it can be exported in an hotel. So if we have a central managed system that now speak with the common auto and API, it can also ingest the data through from our Kubernetes clusters. And of course, what's really, really nice, it can understand everything about our layer 7 application protocol. So DNS issues, SSL, termination issues, HTTP, of course, and it's really, really nice. So let's talk about the last part of this architecture, which is chaos mesh. So when we think about chaos mesh, a lot of the time we're thinking about Chaos Monkey. And Netflix, like famous architecture, and they are genius, they're amazing, about just let's take random EC2 instance, pull it off, and let's see what's happening. We're talking about much better, much more than this. So we want to orchestrate a failure that tests the whole system, not just our EC2 instance. We want to do it, for example, I want to check my pod failure. I want to add to a specific pod when you have any ingress communication, have a latency of, let's say, 150 milliseconds, and see what's happening in the system. I want to hook some kind of changes in my JVM to make sure if it's working or not, or even to do some kind of like back to the future and change my timestamp and see how the system behaves. For example, changing the timestamp, if I'm creating JWT tokens, can create maybe unpredictable behavior of my authentication and authorization system. And to do so, I would like to do it in a safe way, because by the end of the day, we don't want that the chaos technology or framework that we're using will create a chaos. But again, chaos, but manage chaos. And also, it's not just meaning one step. Take a look here. I can create workflows. So for example, I will execute a pod failure. Then, after it's running again, of course, and Kubernetes will understand it's part of the deployment, replica set, it will initiate another one. I will force delete it and see how Kubernetes is handling. So it's not just one scenario that I'm pulling a random EC2 instance. This is really, really important. And now I want to show you a demo that I really, really love. Do you see my screen? All right, so let's start the demo. So I'm using something very, very nice. You can see here in my code. I'm using Demo Magic. Anyone know Demo Magic? So we have to know it. This is really one of the main things that when you're typing in a real demo, is that you make mistakes, you know, to go up and down, Control Alt, find the commands. This is real time, but it's showing you behavior like I'm typing it. So let's run it. So the first command will be open my login page and see my ArgoCD. So let's log into the system. You see it's healthy, it's synced. We see a very, very complex system. I have a lot of microservices, communication, replica set, and blah, 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 blah. This is a really complex system. And it's all managed with ArgoCD. This is the first step that we're doing. The second thing will be, okay, let's take a look on our cluster. It's EKS cluster with 3 nodes, I think it's three large instance. Let's take a look on our pods. So I've created a new namespace microservice demo to host all of the pods. We see that we have card service. This is, again, like the same demos, very complex ordering system. And let's take a look how communication is done. So when we running get SVC, we see that it's cluster IP. So it means like, from what we understand right now, all of these components are connecting to another internally without exposure. So maybe we have an ingress. Let's take a look at the environment. So yes, we have an ingress that's creating an application load balancer in AWS. This is amazing. So let's take a look on the application. So it's going to open my browser, and I think that we're in Texas. We need sunglasses. It's really, really hot. I'm coming from New Jersey. We just bought the items. Let's buy another item. Amazing. I think that we see that application behavior very good. The latency is really, really low. And it's a really nice UI UX experience. So let's continue. So I've installed Pixie. And as you can see here in Pixie, we see three pods called Visor PAM. These Visor PAMs are the data collectors. They are installed as part of daemon stat. On every Kubernetes cluster they create, on every node that they created, the daemon stat is responsible to creating the eBPF agent that will do the instrumentation and get all the information that you got. So this is really, really nice. So let's connect to Pixie, and I was lazy. I use a manager, so Cosmic AI. Let's take a look at the cluster. This is really, really nice. Without intervening, no one in my system, without doing anything, I can see the HTTP service map, because I have now a graph of all relations, because I'm running low level at the core level. I can see statistics about my nodes, about my namespaces, my services, and again, align it with HTTP, but not also when I'm going to click on it, I can have information about how it's running, pod statistics, CPU-based, and correlation. And what's really, really nice is because Pixie is working at, as we said, at the core level, Linux core level, we can have a flame graph. So who loves flame graphs? Anyone? Anyone? All right. So in flame graphs, I can do a correlation between my application, namespace, pod, and container with my actual code. As you see here, I have HTTP handle function to manage HTTP server. And again, I can see the full stack. This is, for me, it's blowing my mind. I can see everything from the hardware till the specific function call without adding any hook to anything. This is kind of amazing. Let's continue. So again, I also want to install Chaos Match, and it's the same thing. You see that we have Chaos Daemon, Chaos Daemon, and what he's doing, he's doing a privileged access to our, for example, I'm going to use Docker-D in order to instrument something at the low level. So for example, if I want to make network latency, you agree that I need to take a look at my IP table and change it So the routing will be, let's say, for example, with 200 millisecond delay. So how am I going to do it? As you can see here, let's see the role. You see that the role need to get access into a very low level of the container itself, and to do it on every aspect of the system. For example, just to patch IP tables and to change them and reload them automatically. And let's create a token. This is my token. This is not fun, but you're creating a token. Let's go into Chaos Mesh. Let's call it demo, and this is a token. And what you're going to see here. So you're going to see experiment that was running, that was checking Redis cache failure, but I want to be active. I want to show you an example. And you have to give me a few more minutes. I have to finish the demo. You see AB, all right, Apache benchmark. I'm running through my, as I say, ingress. So the baseline, as you see here, to do the processing is around, let's say, 200 milliseconds, which is amazing for a system. I would best every system to be it. Let's take a look now on a chaos we created. We see that the chaos is network one. We're creating delay. Our selector will be on a specific namespace and specific service. In this case, this is the product catalog. And I'm just adding 150 milliseconds. It shouldn't disrupt the system so much. Agree? So I'm running it, I'm applying it. And again, this is a CRD. So eventually, you're going to see here in the experiment, another experiment running. And again, amazing, he detected the pod, he ran the instrumentation, he ran the change, he created latency. But let's now check the latency. We run it again, and let's explore if it was different or not. So I'm running it again. Okay, so I see now it's bigger. And yes, it seems like the average median waiting time was around 100 plus milliseconds. So it seems like it makes sense. But now let's tweak it a bit. Let's take another one, and I will just delete the last one. And take a look here, guys. This is another chaos mesh. This chaos mesh just taking another service. So instead of the service catalog, I'm going to focus on the front-end service. And again, I'm just going to add 150 milliseconds. Will it behave the same thing as our catalog? So let's run it. As you see here in the experiment, now we have another one. Again, it focuses on this specific service. But now let's try to run the AB, the Apache benchmark. Let's see, because if I predict it right, this is going to be just a very, very short delay, 150 milliseconds. But what's going to happen? 1 second, 2 seconds, even 3 seconds. Why it's happening? It's even taking more time. So take a look at what's happened here. Now, as we see, the processing and waiting time is 15 times more than the last one. And it means like the change that we think will behave one way can behave differently. But you want to see something even more beautiful? Take a look here. Let's check with the UI. Maybe I'm just wrong. So I'm going to go to the UI. I'm going to click. You see there's waiting time. So of course something happened here. I want to summarize how we can use GenAI also to help us here. Take a look here what I'm doing. So it's very strange. We now have an unpredictable behavior. Why it's happening? Take a look here. What I'm creating here is that I'm using the CLI of Pixie, and I'm getting information about the system. I'm getting the service status, the age, the mapping, the relationship, and I send this information into a GenAI. All I need to do here, and take a look in my code, you can see it here. Do you see my screen? All I'm doing here after getting all the data, I tell him, okay, my system prompt is that you are an export observability system. Your task is to diagnose blah, 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 blah. And in the answer, I'm just asking the question. There is no information about our hint. Analyze why 100 millisecond artificial delay caused. And when you see the response, this is amazing. It tells me that the front-end on-reported latency, which is higher, but there was a call, per call latency to the backend services, advisor, service, product catalog. It's still sub-seconds from the issue, but the aggregation of all these calls created the 2 seconds, 2 plus seconds delay. And this is, I think, and just to summarize, just a second, just to summarize it, I think that this is, in my opinion, very, very important. When we're thinking about breaking stuff, even in a child, when we went to the store and our father or mother tell us, don't break anything, I think we need to change it. I think that changing the way we think about from I have amazing wins at 99% dot to infinity, it's a victory. Let's try to think about differently. If it's going to fail and it's running for 2 years, what's the hell going to happen if it's really going to fail? Will I be able to restore it? So we want to shift from preventive failure to embrace failure. We're going to do it by understanding that chaos is much more than just a failure. And just to summarize, our system will fail. We can learn from it now, or we can learn from it later when it's crashed. And last thing, you can also think about humans, right? Chaos humans. I don't mean we need a person, but think about this thing that you're going to say to one of the SRE. Today, you're not going to be on call. How my system behave, and maybe this one he's a genius, but if he's out of office, for example, no one else in my team can handle the situation. So thank you guys very much. My name is Elad. It was a pleasure to be here, and if you have any questions, I'm here. Thank you guys.